Okay, so welcome back to the course. Last Wednesday also we didn't meet, and yeah, so we are coming towards the end of the course. In fact, today's will be the last lecture of the course. We will do one more small thing today, and that will be the end of it. And we also need to think of grading, etc. So I will mention my slides what I am planning to do. Okay. Yeah, I have written everything in the slides. So what I'm planning to do with the course and with grading, it will come in the relevant slides. We will do a little bit of mathematics before that, and so let's start. So I'll share the screen. Could you please confirm you can see this?
Yes, I can see it.
Okay, fine. So I hope everyone can see. Okay. So today what we will do is a nice result which I like a lot. Rudin doesn't mention this name Bezu, but there is what is called a Bezu ring or a Bezu domain in algebra. So we will see what it is, and what we will show is that the ring of holomorphic functions on an open set. We will prove it for a region, but it's true for an open set also. So ring of holomorphic functions on a region, it is a Bezu domain. Okay, I will define what it is, and we will show that it is a Bezu domain. So another algebraic property of the ring of holomorphic functions. This is what we will do today. So last time we proved the Vystras theorem. So what did it say? What was Vystras theorem? We proved that you can give me a set and a set of points, and then I can cook up a holomorphic function. Zeros are precisely the set that you have given me. You can even prescribe the multiplicities. I can cook up my holomorphic function which has zeros exactly where you have the points that you have given me with the prescribed multiplicities. This is Vystras theorem, and the crucial ingredient was his definition of elementary functions, Vystras elementary functions, and we did some work on convergence of infinite products, and we defined the elementary functions, and we got some estimates for the size of the elementary functions, and using that we could prove it was not very difficult. We could prove that you can have holomorphic functions with prescribed zeros. Of course, the set that you give me should have an important property. What is it? It should not have a limit point in your region omega. So if right, a holomorphic function zeros are isolated. So if you give me a set without a limit point, then I can do this. This is what we have done today, and today what we are going to do, ring of holomorphic functions is a Bezu ring. It's a Bezu domain. It will use Vystras theorem. It will also use Pythagoras theorem. You remember Pythagoras? It was the pole equivalent of Vystras theorem, which we had proved as an application of Runge's theorem. I can construct meromorphic functions with a prescribed set of poles, prescribed multiplicities, and prescribed principal paths. So we will put Vystras and Pythagoras together and conclude this particular fact. So today we will prove that H omega is a Bezu domain. So what does this mean? So Bezu, a ring is called Bezu. Okay. So before that, you tell me what is a PID. So let me put that part. So recall PID, Noetherian, and Bezu. Why don't you tell me what is a PID?
It's an integral domain where every ideal is principal.
Principal meaning generated by one element. So
Yeah.
everything is so if every ideal is principal, you call it a PID. And have you seen Noetherian also, Ariman?
I know the definition of it.
But you know it independently. You did not yet have it, no? In a
No,
course.
no, like the professor has mentioned it at times, but as in he has given us the definition and mentioned it,
In
but
which
we
course?
haven't done
In which course?
algebra 2.
You have done algebra too?
I'm doing that this semester.
Ah,
It's
now.
going on.
Okay,
Yeah.
okay. But then this should be a part of algebra too, no?
No, as in we didn't do much about it.
Okay. But that means in no other course you will see it, no, unless you take an elective.
Yeah, I
Algebra
guess
is a
so.
compulsory course or an elective?
Elective.
Algebra 2 is already an elective. Okay, fine. So what is Noetherian?
One thing is that every ideal is finitely generated.
Yeah, so let's take that as the definition. There are some equivalent definitions. So every ideal is finitely generated. So PID is every ideal is singly generated, and Noetherian is a slight generalization. So every PID is Noetherian, right? Noetherian is every ideal is finitely generated. Now we come to the definition of Bezu. So these other two you already know, and Bezu is, I'm not saying that every ideal is finitely generated. I'm not saying that every ideal is singly generated. But what I'm saying is every finitely generated ideal is singly generated. You get the definition? So PID, every ideal is singly generated. Noetherian, every ideal is finitely generated. But Noetherian need not be PID. In Bezu, every finitely generated ideal is singly generated. But it need not be a PID because every ideal need not be finitely generated. But if an ideal is finitely generated, then it is singly generated. Is the definition clear? So a wonderful example is H omega, and that's what we are going to prove today. Is the definition clear to all of you? So in a Bezu domain, there may be all kinds of ideals. There may be ideals which are not finitely generated, infinitely generated. But if an ideal is finitely generated, then you can show it is actually generated by a single element. And H omega has this property. So we'll show that today. So here is an assignment. So what we are going to show today that it is Bezu, but do not use that fact. So assignment is coming before we are doing it. Prove or disprove that H omega is Noetherian. Okay, so think about it, and this is your assignment. You only need to give some points, so you don't have to give a full proof. I'm not interested in a full proof. Okay, just to show that you got the idea, you got the definitions right, and you have thought about it properly. So if we are assuming today's result, then uh, yeah, it depends on whether you say prove or disprove. Maybe this part we can even discuss. What do you think? Just a hunch. You don't need to prove it. Is it yes or no? What do you think?
It's not
Who's saying this? Not? Ariman?
argument.
You're saying it's not. You know this or that's your feeling?
No, that's my feeling based on it. I mean,
Feeling.
otherwise we would prove that result, right?
Okay. Well, yeah, good. Someone else make some comments. Mamata, you want to take a guess?
I'm not sure. Like I haven't.
Yeah,
Like
but
I have no idea.
suppose you have to pick. So Ariman said maybe not. What do you think?
I think his point is correct. Like if it is true, then we would have proven that.
Okay, fine. Omkar, maybe you already know this.
Yeah, I mean, I got a proof just now. I
Oh,
had seen
okay.
similar.
Don't give the proof. It's an assignment. But what's
Yeah,
your answer?
yeah. I think it is not Noetherian.
And you are proving it. Okay, good. So proof you submit in Google Forms. Okay.
Okay.
Okay, so the answers are already here. In fact, Omkar said, Ariman said, Mamta said, it's not Noetherian, and you have to prove it, but don't assume it's Bezu. Okay, because if you assume it's Bezu, then what do you need to show in order to show that it's not Noetherian? You just need to show that it is not a PID. But that's not what you should do. You should, without assuming that, you should show that it's not finitely generated. Okay, so that's assignment 6. Let's go ahead. Yeah, so as I said, today is our last class. So I hope most of you are here. We won't be meeting again. So let me see. 17 students are there. So that means this is less than our usual strength. So I request people who are here, who have friends who are not here, just to WhatsApp them, if possible, come, because we are not going to meet after this. So you can just message your friends to come within next 1 hour. Okay, so that I can say bye to everybody. So today is our last class. Actually, tomorrow also, I think it's a week of instruction. So we have one more class really, but I don't think I will take it because this is a good point to stop. So we will not have classes in the next week, and the week after that is your exam week, and we have decided in our last class that we will not have an exam either. Okay, so we will not have an exam. So this is assignment 6, and I will make my grading scheme clear towards the end in the last slide also. So what I am planning is these 6 assignments. So maybe some initial assignments were already for 10 marks, but then maybe they were assignments for 5 marks. But the 5-mark assignment also I will rescale to 10. So overall, the 6 assignments will have 60 marks, 6 into 10, and I will give one more assignment at the very end, and that will be for 40 marks. Okay, so that will be the NSEM assignment, and you submit whenever you can, and I will do some grading. Okay, so we will not have class in the next week and no exam. But I will just mention what I usually do. I usually do a bit more than this. So we started late, we are ending earlier, so we are not covering what all I typically do. But not much is remaining because we were using Beamer and slides. Things have gone a bit faster than on the board. So on the blackboard, maybe I would not have covered this much in these many classes. Uh, so though we get many more classes, we cover only a little bit more usually. And 3 keywords are the following things which we do usually, which we are not doing this time. One is called Jensen's formula. It is there in this chapter of Rudin itself. So I'm following everything blindly from Rudin, right? There's nothing that I have done which is not there in Rudin. Jensen's formula. So this is about zeros of holomorphic functions. We have already seen Vystras theorem, and this is another very beautiful formula to count the number of zeros. And in the next chapter, there's something called the Monodrome Theorem, which I have done sometimes and I have not done some other times. And of course, the famous Picard Theorem, Little Picard Theorem we usually do. Once I had done Big Picard Theorem also, but usually I don't do it. So these things, those interested, please read Rodin. Okay. These are all very well explained there, so have a look if you are interested. Otherwise, it's okay. But as all of us know, this was an unusual semester. All of us have gone through a lot of hardships. In fact, many of you had many more hardships than me. Therefore, I think it's okay. It's an elective. You have taken this out of some interest. And you have seen, you have got a flavor of the course. You have got many things. You have seen many things which you hadn't seen before. I think it's enough. We should not take all these things too seriously. It's okay. So it's a good time to stop. And so we will do this beautiful result that is a Bezier domain, and we will stop there. Okay. So yeah, this was an unusual semester. So I think whatever we have done is enough. And that's good. Yeah. So let's start. So there is what is called an interpolation theorem, which is what we will do first. And as a corollary, we will do that H omega is a Bezier domain. So let omega be an open set in C, and let A be a subset without a limit point in omega. Okay. And now we are going to claim that there is a holomorphic function. So we already know that there is a holomorphic function with zeros at A. But we are going to claim something slightly different. You can, yeah, I'm going to claim that there is a holomorphic function whose values at this set A, right? You have given me the set A, and I'm going to say that there is a function f, and if alpha belongs to A, then I can make sure that f of alpha is a value that you have given me. So I can construct a holomorphic function with prescribed values. Okay, is that obvious? You give me a point, you give me a complex number, and you give me a complex numbers, and I'm going to say that I can construct f such that f of alpha is the number that you have given me. So suppose you give me let us say C alpha. For each alpha in A, you prescribe a complex number C alpha, and I'm going to say that there is an F such that F of alpha is C alpha. Such an F can be constructed. Is this obvious?
I think using Mittag-Leffler and
No.
Vystras.
Yeah, then it's not obvious, right? That's what we are going to do. But just Vystras, it's not obvious, right? Because F minus C alpha, these are different functions. So yeah, so it's not all that obvious, but you're right. We are going to use Vystras plus Mittag-Leffler and combine, and then we will get this. It's not very difficult to do once the ideas are there. So we are going to show that there is a holomorphic function with prescribed values at these points, but a bit more. We are going to show that we can also prescribe the values at the derivatives. So with prescribed values at finitely many derivatives. So what does this mean? This means that we have alpha in A. If you take, I can prescribe, and you can also give me M alpha, a natural number associated to each alpha. You can give an M alpha, and you can also give, some complex number Wn alpha. So you are giving me many complex numbers. To each alpha, there is an associated number M alpha, and then you are giving me that many M alpha, many numbers Wn alphas. Here n varies from, so I haven't written it here, n varies from 1 to M alpha. So if M alpha is 10, I'm giving you 10, these are 10 complex numbers, 1 alpha, 2 alpha, up to 10 alpha. Okay, such that the nth derivative at alpha is prescribed. So I can make sure that this is the value at the nth derivative. Fn alpha by n factorial is that complex number. So this is the meaning of saying I can construct a holomorphic function f with prescribed value at finitely many derivatives. So associated to alpha, if you give, it has to be 1000, then 1000 derivatives you can prescribe values. Okay, so this can be achieved. So this is what is called the interpolation theorem, and we will be applying both Vystras and Mittag-Leffler. And how do we do this? So by Vystras, there is a holomorphic function g whose zeros are precisely this set A. Why? Because A does not have a limit point. That's all that we needed. So A does not have a limit point in omega. Therefore, there is a holomorphic function by Vystras whose zero set is precisely g. I can also prescribe multiplicities, and let me construct so that the multiplicity at alpha is m alpha plus 1. So the order of g at alpha, the multiplicity of g at alpha, maybe order is not the word, order we usually use for pole. Anyway, multiplicity of g at alpha is m alpha plus 1. The claim is that associated to each alpha, there is this kind of a function. So P is for principal part. So this resembles a principal part. So J going from 1 to M alpha plus 1, some coefficient by Z minus alpha power J, such that if you multiply G and P alpha, you will get this. These are the numbers that you have given me. These are the complex numbers that you have given me. These are the prescribed values. So up to M alpha you have given me, and after that something or the other, I don't care. Okay, so the product has this kind of a power series expansion in some disk with center alpha. So in a small disk with center alpha, I can, to associate it to alpha, there is such a rational function such that the product has coefficients. The first m alpha many coefficients of the product is what you have given me. There's a typo here, I will correct it to comma. Okay, so in some neighborhood of alpha, in some disk around alpha. Suppose this is done, then you are done. Then you are done. Why? Because we have to show, see, what is the, suppose you call this a function f. If this is the function f, then what is the property, what is the nth derivative at alpha by n factorial? It is exactly the coefficient, right? But that is only for alpha. We want for each alpha simultaneously. How do you achieve this? Take this claim to be done. Suppose this claim is done. then at alpha you have got what you wanted. At alpha, if you have this P alpha, and if you consider this product to be F, then F nth derivative by n factorial is precisely Wn alpha, because it's a corresponding power series expansion. Okay, so there is a small typo here. This is not Z. What is this? It's centered around alpha. This is Z minus alpha. Z minus alpha whole square, etc. I'll correct the typo before I put it on Moodle. This is Z minus alpha, Z minus alpha. It's a power series expansion around alpha. Then f nth derivative at alpha by n factorial is precisely the coefficient. But this is at alpha, whereas we want something which works for each alpha. And how do you finish this problem? Suppose this claim is done, then is that it?
Yeah, then we can use Metag-Leffler.
Then you can use Metag-Leffler. So the only problem here is I cannot call this product to be F. That depends on alpha, but you can use Metag-Leffler and get something simultaneously for all the P alphas. So suppose this is done, then the result follows by Metag-Leffler, because you can construct a meromorphic function with principal parts P alpha. And you can take that function times G and take F equal to GH. So F equal to GH, around alpha, it is GZ P alpha Z, the behavior. And therefore, at alpha, the derivative is the correct thing. And another alpha, the behavior of GH is for that P alpha. And therefore, you have got all these simultaneously. So it is Vystras plus Metag-Leffler. So it's a beautiful thing. You can prescribe finitely many derivative values. You can prescribe values. You can construct a function with prescribed values for finitely many derivatives. Okay, so we just need to do this one, and that is easy. That's just elementary manipulation. In order to prove, so we will take alpha equal to 0. It's without loss of generality. It's just notation. And M is M alpha. And we need to find Pz, which is C1 by Z plus C2 by Z square plus etc. Cm plus 1 by Zm plus 1 with that property. What is the property? G times Pz is what you have given me. So what you do is write down the power series expansion of Gz. Gz will have a power series expansion B1 Z power m plus 1. Why starting with m plus 1? Because at 0 there is a 0 of order m, so it starts with z power m. I mean z power m times something, so it starts with z power m plus 1. First m coefficients are 0 because it has a 0 of order m. So gz is b1 z power m plus 1 plus etc., where b1 is what? What can you say about b1?
Non-zero.
B1 is non-zero because this is the order, this is the multiplicity. So B1 is non-zero.
But the given thing has 0 m plus 1, right? Given Gz has order m plus 1, right?
Correct. That's yeah. Yeah, that is why it is B1 is up to m plus 1, right? It is 0 of order m plus 1. That's why this is m plus 1. Yeah, correct. You are right. Yeah. 0 of order m plus 1. That is why the m plus 1 coefficient is non-zero and all the rest are 0. Absolutely. Z power m plus 1 comes out. 0 of order m plus 1. Yes. And now what you need to do is just multiply, right? So G times P. So this times this is what has coefficients what you have given me. So we can solve for the C's. C's we don't know. We want to show that there exists P, which means there exist these Ci's. So we can solve for the C's from this product. This is given. Wi's are given. This is W1 alpha, W2 alpha, etc. Alpha is 0. Therefore, I am deleting it from the subscript. Just notational simplicity. So W0, W1, etc. Wm is given to me. The rest I am not bothered. And you have to solve for C's, but the B's are given to you. So you can, compare the coefficients and solve. Because B1 is non-zero, you have a starting point, right? Because what is this product? Gz times Pz. What is a constant term of this product? Constant term of this product is B1 times Cm plus 1, right? And B1 times Cm plus 1 is W0. Therefore, you have solved You have got Cm plus 1 to be W0 by B1, which makes sense because B1 is not 0. So you have solved Cm plus 1. Now you can look at the coefficient of Z. From there you can solve for Cm and you can recursively solve for all the Ci's. So you are done. So you can all solve for the C's from this since the B's are given and B1 is non-zero. And that's it. Then you apply Pythagorean. So this is done. So I just need to remember to correct two typos here. First typo is this is a comma and the other typo is it is z minus alpha square. Okay. So this is what we are calling interpolation result. You can get the prescribed values for finitely many derivatives. Like that you can construct a holomorphic function. Now let's do Bezier. Okay. So let omega be a region. Actually, Rudin makes this remark that once you prove for regions, you can prove for any open set also. Then you cannot say Bezier domain, you have to say Bezier ring. But let's do it for a region, Bezier domain. Right? Only on a region we are saying it's only on a region we know it's an integral domain, right? Yeah. Is that true? Do we need integral domain for zeros to be isolated?
Yeah.
Yes.
I mean, we need region for zeros to be isolated.
On one connected component, you can take identically 0. Yes. So Bezier ring is true in general, but we are using the word Bezier domain. So we will take a region. So let omega be a region. So what do we need to show? Bezier domain, what is the definition? If you have a finitely generated ideal, you should show that it's principal. So take a finitely generated ideal. This is my notation. Ideal generated by G1, G2, etc. Gn. So suppose these are holomorphic functions on omega. So you are considering a finitely generated ideal, a random finitely generated ideal. You should show that it is principal. So you have to show that this is generated by a single holomorphic function. And for this, you take a phi holomorphic function such that at alpha is any element in omega, and at alpha the order of phi, you take the orders of the order of alpha at gi. For each you have been given n functions, and given a point alpha in omega, you look whether alpha is a 0 or not for each of these functions, and if it is a 0, you take the multiplicity of gi at alpha and consider the minimum. And you construct a phi such that the multiplicity of phi at alpha is precisely that. This can be done, right? Why can you? How can you do this? So this is for each alpha. What is the one word proof that this can be done? Right, you take all points in omega, and you are saying that right, this has some content only if alpha is a 0 of one of the gi's. No, I mean if alpha is a 0 of all of the gi's only, this has some content, right? If alpha is not a 0 of one of the gi's, then what is the multiplicity of gi at that alpha? It is 0. And even if other gi's vanish, the minimum is 0. So you don't have a 0 for phi there. So what you need to do is you have to take common zeros of all the gi's. And if you take the set of common zeros of all the gi's, that's a set without a limit point, no? Because these are zeros of holomorphic functions. So that's a set without a limit point, and and you take this to be the multiplicity, and then by Vystras you can construct a phi such that the multiplicity is precisely that, right? Agree? So this is just Vystras. So by Vystras theorem, you construct a phi with this property that the multiplicity of phi at alpha, right? You can construct a holomorphic function with prescribed set of zeros with prescribed multiplicity. So you consider the collection of common zeros of gi and let the multiplicity be the minimum multiplicity of whichever GI has the minimum order. You take that and let that be the multiplicity, and then apply Vystress to that collection and those multiplicities. So you have constructed a holomorphic function with precisely this multiplicity at alpha, and do this for each alpha. If alpha is not a common zero, then there is no content to this. Okay, so this is Vystress. And now consider small gi to be capital GI by phi. Is small gi holomorphic?
Yeah.
Why?
Because whenever phi does have a zero, gi will have a zero of at least that much order.
Is that greater than or equal to? So that zero will get cancelled. So this meromorphic function has removable singularity. So it is holomorphic. So GI, all these GIs are holomorphic. So by construction, GIs are holomorphic, and GIs have no common zero also. Agree? You see this? GIs have no common zero because of this minimality here. Right? If G1 has a 0 at alpha of order 2, G2 has 3, then phi has 0 of order 2. So G1 will have no 0 at alpha, G2 will have a 0 of order 1. But G1 will not have a 0. So by taking minimum and dividing, the GIs will have no common 0. If there is a 0 for some of those, at least one of the GI will not have a 0 there because you are dividing by the minimum. Okay. So clear, no, Ariman?
Yeah, it's like dividing by the GCD sort of a thing.
Dividing by exactly, yeah. So it will have no common zero, and then we are going to claim that the ideal generated by small g1, small g2, etc. is the ideal generated by 1. What is the meaning of ideal generated by 1? What is 1?
The whole ring.
Yeah, 1 is a constant function 1, which is the multiplicative identity. So ideal generated by 1 is a whole ring. So we are going to claim that this is the whole ring. If this claim is true, then we are done. Why? Because assume the claim. Suppose the claim is proved, then it follows that the ideal generated by capital G1, capital G2, etc. is what? If these quotients generate the full ring, then what will be this one? Take a guess, and the guess will be correct. There's only one candidate on the slide, and therefore that has to be your guess, and then it's easy to see that that guess is correct.
Generated by phi.
Ideal generated by phi.
Correct, because these are G1 by phi, G2 by phi, etc. and they generate 1, therefore this will generate phi. And that's what you wanted to show, no? You wanted to show that any finitely generated ideal is singly generated, and you're getting a single function which generates. Okay, so what do we need to prove now? Everything is done except this one. So the claim that we need to prove is, right, up to now it's just elementary things. Okay, Vystress we use once, and this was an elementary calculation. And what we need to prove is, if you take a collection, a finite collection of holomorphic functions without a common zero, then the ideal generated by that is a full ring. That's what we have to show. Okay, so that we are going to show now. So every finitely generated ideal is principal. So we prove the claim that if you take a collection of holomorphic functions without a common zero, then they generate the full ring by induction. We are going to prove this. Where will the induction be? Take a guess. If you are proving this, where will the induction be?
On n.
On n, on the number of generators. So by induction on the number of generators n. N equal to 1. What do we need to show?
That it's a unit.
Yeah, so GIs have no common zero, meaning if you have a single function that has no zero, right? And if it is not, if it doesn't have a zero, then it's a unit, right? Because you can take 1 by G. Correct? So n equal to 1 is done. N equal to 1 is obvious because you have a function without a zero, so 1 by G is there, so it's a unit. So n equal to 1 is done, and now suppose you have up to assume induction by induction assume that up to n minus 1 you have already done, and now you have to show for n. Okay, so suppose g1 etc. gn are holomorphic functions without a common zero. Okay, and we are assuming induction up to n minus 1 we know something. Is it true that if I take g1 up to gn minus 1 they don't have a common zero? That may not be true. The n functions together do not have a common zero. Up to n minus 1 if I take, they may have a common zero, but now I have a strategy, to construct something without common zero. The earlier strategy, take the minimum and take those multiplicities, take Vystras, divide by that. So let's do that. Okay, so there exists a phi in h omega such that m of phi alpha, the multiplicity of phi at alpha is minimum of m of gi at alpha up to n minus 1 I am doing. Okay, 1 to n minus 1, you take this minimum for each alpha in omega, and this you can do exactly earlier by Vystras. But I am doing up to n minus 1. G1 up to gn minus 1, you take the common zeros, right? If you take the full thing, then there is no common zero. But I'm taking up to n minus 1, take the common zeros, give the minimum as the multiplicity, prescribes those things, and take a phi. This can be done by Vystras. We have already done this trick earlier. And consider up to n minus 1, consider the quotient fi to be gi by phi. You agree now that fi's have no common zeros, right? f1 etc. fn minus 1, these functions have no common zero, and therefore what can you conclude? What can you conclude? Now we know that f1, f2 etc. fn minus 1, they have no common zero. Therefore
FIs generate the ring.
FIs generate the full ring by induction hypothesis. So FIs are holomorphic as earlier, removable singularities, and they have no common zero by construction, and therefore they generate the unit ring, the full ring, F1 etc. Fn minus 1. Okay, and we are more or less done. Well, I mean, the crucial step is remaining. Up to now, we haven't used the interpolation theorem, but what we have done now is what? We have reduced the case of n to 2. Okay, why? Because if you take g1 etc. gn minus 1 comma gn, that is the ideal generated by phi and gn, because as earlier, right, gi by phi generate 1, so the gi's up to n minus 1 will generate phi. Therefore, the whole gi's gn minus 1 comma gn will generate phi comma gn. And moreover, gn of alpha is not 0 whenever phi alpha is 0. Why is that?
Because the original G's had no common zero.
Original G's had no common zero. If phi of alpha is 0, that means g1 of alpha is 0 up to gn minus 1 of alpha is 0. Therefore, gn of alpha is not 0 because original gi's have no common zero. And this is important in the next step, that gn alpha is non-zero. Whenever phi alpha is 0 will play a role in the very next step. We are going to, so this is because original gi's have no common zero. We are going to claim that there exists an h in h omega holomorphic function such that you consider 1 minus h times gn, this gn, and at alpha, the multiplicity is greater than or equal to the multiplicity of phi at alpha for each alpha in omega. This is the interpolation theorem. This is because of the interpolation theorem. So what do you need to do for this? You just want this greater than or equal to. So you're going to prescribe, you're going to construct h by prescribing finitely many derivative values. That's all that you need in order to do this, right? So you already have phi, and consider any alpha in omega, and what do you need? So what is multiplicity at alpha of a function? Yeah, so this is right, 1 minus hgn has a 0 at alpha means what? H of alpha times gn of alpha is, right, 1 minus hgn at alpha is 0. So h of alpha times gn of alpha is 1. So in other words, it is prescribing the value at alpha for h. No, h of alpha should be 1 by gn alpha, right? And gn alpha is non-zero if phi of alpha is 0. So if phi of alpha is 0, this is at least 1. And in which case I can prescribe h of alpha to be 1 by gn alpha, so that this is a 0. But how do I make sure that the multiplicity is higher than this? That depends on prescribing what? That
The
depends on
derivatives.
prescribing the derivatives. And that derivative value will depend on the value of gn prime, etc. But whatever it is, because of gn alpha is non-zero, I will get the I will be able to get quotients which are well defined, and I can prescribe the appropriate values so that I can get an edge such that this property is true. Okay, so I haven't written down all the details, but the idea is clear. Suppose this is 1, suppose this is 0, then I'm not bothered. If this is 1, I will construct h such that h of alpha is 1 by gn alpha. If this is 2, I will construct h so that h of alpha is 0 and h prime alpha is 0. But both h alpha and h prime alpha, I can see what it will be. No, this at alpha is 0 and this prime at alpha is non-zero. But this prime at alpha, when you do, it will involve h prime alpha only. So that particular value also you prescribe. So you prescribe values, finitely many values, so that you can construct an edge with this property. Okay, this is where the crucially we have used interpolation, which uses both Vystras and Mittag-Leffler. Okay, the idea is clear. So you can construct an edge holomorphic such that multiplicity of 1 minus hgn at alpha is bigger than this, where you have crucially used the fact that gn of alpha is non-zero whenever phi alpha is non-zero. So you have used the fact that these have no common zeros in this step. Okay, so you're done. This is by interpolation theorem, and now you're done because you consider the function 1 minus hgn divided by phi. This is holomorphic, right? Because of this condition, 1 minus hgn has, wherever phi has a 0, this has a 0 of higher order, therefore this has removable singularities. So this is holomorphic. It has removable singularities. So what have you proved? You have proved that phi comma gns, the ideal generated by phi and gns, what now? What is ideal generated by phi and gn?
If we rearrange, we'll get that it has 1 in the ideal.
It has 1 in the ideal. Yeah. Therefore, the ideal generated by phi and gns, the full ideal. So therefore, ideal generated by phi and gn is the full ideal, and therefore you are done, right? So you have proved that by interpolation theorem. You have proved that this is the full ideal. The full ideal meaning this is the full ring, and therefore this is the full ring, and this is what you wanted to show. If they have no common zeros, it is the full ring. They have no common zeros, it is the full ring. No common zeros, then it is a full ring, in which case you have shown that any finitely generated ideal is principal. So it is a very beautiful result. So it's a, have you ever seen this kind of a ring in your ring theory? See, PIDs, of course, this is true. PID is obviously Bezout, right? No, PID is obviously Bezout, no, because every ideal is principal, and in particular, every finitely generated ideal is principal. So PID is Noetherian, PID is Bezout. So there is this branching out. PIDs are Bezout, PIDs are Noetherian, but Noetherian need not be Bezout. Can you give me an example of a Noetherian ring which is not Bezout?
I think ZX would work.
ZX is not a PID, right?
Yeah.
You can take a prime number and you can take the variable X, and that ideal has at least 2 generators. It has exactly 2 generators, and that is not singly generated, so but it's Noetherian. So it is Noetherian but not a PID. No, but what was the question? Question was not Noetherian but not a PID. Yeah, therefore it's not Bezout because it's a finitely generated ideal and it is not singly generated. So it's not Bezout. Now the question is, have you seen a Bezoar ring before this? I mean, other than PIDs. PIDs are trivially Bezoar. Have you seen a non-PID which is Bezoar? So this is an example of a non-PID which is a Bezoar, because in the assignment you are going to show that it's not Noetherian, and therefore in particular it's not a PID. So this is non-trivially Bezoar. Have you seen some other example? Maybe you haven't. Yeah, I don't think you would have. So, I mean, finally, so in our complex analysis results in the last lecture, I am doing a little bit of algebra, and I am giving you, a definition, new definition, and a brand new example, which is this full course actually, right? This example involved the whole complex analysis course, no? We have used in order to prove this, we used the Vystras and Mythaglepler, and Mythaglepler uses Runge. And Runge uses all kinds of things. I think we have used everything in order to prove a brand new example of a brand new definition of an algebra result. And this is an example of what is called a Bezoar domain. I haven't put it in the slides, but let me say that there is another famous, I have time, so let us say a few words, okay? Those interested in Google and find out more. Or I myself can Google if you want. No, let's leave it. You can do it. Okay. So another famous example of a Bezoar domain is what is called notation is Z bar. Z is integers and Z bar. What does that mean? So Onkar certainly knows what Z bar is, but others I'm not sure. But let's try to guess. Ariman, you want to take a guess? If I have a notation Z bar, what could it mean? You can make wrong statements, no problem, if you don't know. What could it mean notationally?
Like it's small z.
Capital Z, integers. Bold Z, with that extra bar. Integers, set of integers is Z, no? I'm putting a bar here on top. What could be that notation? This is something that you might not have seen, so I'm just trying to guess how you may make a guess.
The closure will not make much sense.
Yeah, closure only, but what closure? Oh, okay, closure not as in topology. Not as in topology. Closure as in, you have seen closure in your algebra also, no?
Like the field of fractions sort of a thing.
No, in field theory you have seen a closure, no?
Yeah, algebraic closure.
Algebraic closure. So what is algebraic closure? If you have R, real numbers, what is R bar?
C.
C. And what is Q bar?
The subfield of C, which is all the algebraic numbers.
Algebraic numbers. So Z bar is, because Z is not a field, it's integers. Okay, by the way, we have mentioned this. In fact, you only corrected me in something that I said, that it's an algebraic integer and not an algebraic number, etc. So you know algebraic integer. And this you remember long back. Yeah. I mentioned this Piso Vijayaraghavan thing. Yes. So you know this. So Z bar is the set of all algebraic integers. Okay. So Z bar is set of all algebraic integers. So what does that mean? It should satisfy a monic polynomial with coefficients
from Z.
From Z. Okay. So all integers are of course algebraic integers. Rational numbers are algebraic integers precisely when they are integers, and non-integer but algebraic integer, standard example would be root 2 because x square minus 2 it satisfies, I because x square plus 1 it satisfies such things. Okay, 1 plus root 5 by 2 because it satisfies x square minus x minus 1, etc. So set of all algebraic integers is Z bar. Okay, is that a ring?
Yeah.
So that's not obvious, by the way, but it is. I mean, you need to do a little bit of work in order to show that, it is closed under addition and it is closed under multiplication. And it's of course an integral domain once it's a ring, right? Because there are no zero devices. These are characteristic zero stuff. Okay, so it is an integral domain, and Z bar is another beautiful example of a Bezier domain. Non-trivially, it's not a PID. It's not Noetherian. So Z bar is not Noetherian, but it is also a Bezier domain where the proof is a little bit more work than this maybe, but it's standard. It follows from what is called class field theory, which is an advanced algebraic number theory. So there's an advanced algebraic number theory thing called class field theory. We don't even have an elective on that, so only if you're doing PhD in the relevant subject you will learn it. And one of the famous results in early part of class field theory says exactly that every finitely generated ideal is principal in Z bar. But what is interesting is you have to take Z bar. So you have to take algebraic integers in Q bar. So Z bar is nothing but algebraic integers in Q bar, right? If you take a finite extension of Q and if you take algebraic integers belonging to that finite extension, this property is not true. It need not be a finitely generated ideal need not be a PID. So if you take a finite extension of Q, let's say Q root 2, and you can take algebraic integers belonging to Q root 2. Similarly, you can take any finite extension of Q and you can take algebraic integers belonging to that finite extension. It is true that that is Noetherian. So ring of algebraic integers in a finite extension of Q, finite, underline finite, in a finite extension of Q, if you take ring of algebraic integers, that is Noetherian, but that need not be a PID. It may be a PID, it may not be a PID, depending on which extension you have chosen. And Onkar, maybe if you remember, you can give the keyword here. When it is a PID, what is the number? What is one word that we have seen? Onkar?
Yeah, I'm just thinking.
So this was the initial month of algebraic number theory. A finite extension of Q is what we call a number field, right?
Yes.
And if you take the ring of algebraic integers in a number is Noetherian.
Yeah.
But it may be a PID, it may not be a PID. What we know is it is a PID if and only if it is a UFD.
Yeah.
If and only if. And it is a UFD precisely when the word is class number. Class group and class number. And it is a UFD precisely when the class number is 1. But class number is a finite number, it may be higher than 1. So if it is higher than 1, that means it's not a PID. If it is equal to 1, it's a PID. But we have seen examples of class number bigger than 1. Yeah, when I say it, you remember, no?
Yeah.
So we have seen examples of class number bigger than 1. The most basic example, I think, was Q root 5. Right?
Yeah.
So to everybody coming back, so if you take Q square root of 5, these are all numbers of the form a plus b root 5, where a and b are rational numbers. The field and here 5, for example.
Is it -5 or
Minus, maybe I have in mind 6 equal to 2 times 3. And it is -5, right?
That's the -5 one.
Yeah, -5. So 1 plus root of -5 by 2 times 1 minus root of -5 by 2 is 1 plus root of -5 by 2 times 1 minus root of -5 by 2 is 1 minus -5 by 2. 6 by 2 is no.
We'll get 6 by 4. We'll get 3 by 2.
Yeah, so I don't want to take by 2 maybe. 1 plus root of -5 times 1 minus root of -5 is 6, no?
Yeah.
Yeah. And the question is in z root -5, I think that's a ring of integers. Z of square root of -5 is a ring of integers. And 1 plus root of -5 is an algebraic. Yeah, 1 plus root of -5 belongs there. So 1 plus root of -5 is an algebraic integer. 1 minus root of -5 is an algebraic integer. And the product is 6. But 6 can also be written as 2 times 3. You should also show that 1 plus root minus 5 etc. is an irreducible. So you can write 6 as product of primes in two different ways. So it is not a unique factorization domain. In particular, it's not a PID. So class number is not 1. So ring of algebraic integers in a finite extension of Q need not be a PID, though it is always Noetherian. But that's not what I'm saying here. What I'm talking about here is Z bar, which is ring of algebraic integers in Q bar. And Q bar is not a finite extension of Q, right? It's an infinite extension. Q bar over Q, the degree is not finite. Therefore, the general results from algebraic number theory about class number, about Noetherian, etc., will not apply. And it's an example of a non-Noetherian ring. But this fact is true that it is Besu. If you have a finitely generated ideal, it's principal. These are very two different fields, right? One is algebraic number theory, you are dealing with numbers, and the other is complex analysis. But the two basic examples of Besu domain, one is from algebraic number theory and one is from complex analysis. This itself indicates that maybe there's some connection, and this connection is what I said maybe in one of the classes. I said there is what is called, some theory in the name of a mathematician where there's a dictionary between complex analysis and algebraic number theory. You can use the dictionary. Once you have a result here, you can use the dictionary and you can guess a theorem, and then you will have to prove that theorem using the methods of that area. If you guess a number theory result using a result in complex analysis via that dictionary, finally that number theory result you will have to prove using number theory techniques. Other way also, maybe it is true. So there's a dictionary, and do you remember that word? This came in one of the lectures I just mentioned.
Nevanlin or something like that.
Nevanlin theory. It is called Nevanlin theory. In fact, I mentioned a Fields medalist whose advisor's name we saw when we were doing strong form of Vystras theorem. I said it is from a 1962 book by somebody. We went to Wikipedia and all that. Theodore Esterman or somebody, Esterman I think. And I said one of his students got a Fields medal, Klaus Roth. And I think Roth is famous for this. Some of his works in number theory is motivated by some classical works in complex analysis. So Roth's theorem is an important example which went on to get a Fields medal actually. Okay, so yeah, so anyway, so forget Z bar and all that, but you have got a new definition in algebra and you have got a beautiful example, a non-trivial example of such a ring. And this is what we have been studying throughout this semester. It's a good point to stop. And this is the NSEM assignment 7. So not much maths, but you should know some plain English. Roughly 300 words. You can go maximum 500, but don't go beyond that. It will be difficult for me to read everyone writing so much. Roughly 300, 250, 300 words you aim for. Write a short essay in plain English. Very minimum mathematical symbols you can use. You may have to use a little bit. Otherwise, it's difficult to write something about mathematics. Use very little. Don't use as much as possible. Use plain English and try to convey what you have got from here. Of course, you will have to make a choice because otherwise there's so much to write. So write a short essay, roughly 300 words. At least 150 you write and don't go beyond 500. Aim for 250, 300. About what you have learned from this course in general and your favorite topics from this course. So you may have to make some choice, If you have learned everything, then, it's difficult to write everything. So then you make a choice. On the other hand, certain parts only you have learned and certain other parts you have not learned, then it's easy for you. You have to write only on the part that you have learned. Okay. Details so that, you're not just saying I like Riemann mapping theorem and nothing else. I like Vystras theorem and nothing else. That will be, just 5-6 words. That's not enough. Give some details. Okay. So this is an assignment for 40 marks. So we will have 100 marks. 6 into 10 plus 40. And based on that, I will do some grading. So first 6 assignments. So some of the assignments which were for 5 marks, if I have given 3 out of 5, that will be 6 out of 10. I will rescale it to 10 marks. And assignment 7 will have 40 marks. And based on that, I will do the grading. And that's it. So let's see whether some more students have come. Yeah, good. So 20 people are here. I think class strength is 22. So other than 2, everybody is here. 2 people who are not here. Okay, so only 1 person is not here, maybe Saurav Kumar. So please tell him that the class is over. Oh, Chirag is here. So then that means 1 more person is not here. Good to see you, Chirag. Chirag, hi.
Hi, sir.
Yeah. So though you have dropped the course, you have come because it's the last class.
No, sir, I haven't dropped this course.
Oh, I approved your dropping.
No, that was like I had taken another course. Like I dropped that course.
Okay. So, but I said I have approved, so I don't know whether what does that mean. Now you have to submit another letter saying that you haven't dropped.
No, I haven't dropped this course. Have I?
I clicked something that was not MA521.
No, that was not this course, sir. So that was another course. So I haven't dropped this course.
Oh, I thought that was 521, and you were not coming to so many classes, so I thought you dropped.
No, sir, because like I was just after I realized there were like the videos were getting uploaded to YouTube. I didn't like
Okay,
like
fine.
I could see everything on YouTube.
Okay, good. So you are back and you are here. I thought you dropped and still you came because it's the last class, and I was very touched. So you are a regular student. Okay, good. Yeah. So okay, so most of you are here. So that's it. And yeah. So this is how the grading will be done. And so assignment 6, assignment 5 deadline is over. Assignment 6, let's keep a quick deadline. Assignment 6 so today is Friday. Assignment 6 you submit by tomorrow. That's okay with everybody? Tomorrow night, yeah? Assignment 6. Assignment 7 is NSEM assignment. So NSEM assignment you can write during your NSEM week. So I will wait for NSEM week to be over. So you have a lot of time for assignment 7. So we may have a standard NSEM date. Maybe those 3 hours you can take to write this thing, up to you. So NSEM assignment deadline is whenever is our scheduled NSEM, that night will be the deadline for this. So I don't remember the date. So I think NSEMs are starting on 21st. So that week is the NSEM week. Our exam will have a particular date. We don't have an exam. This is your open exam. And so you take those 3 hours to write this. That may be a good way to get it done. So this will be NSEM and this will be for 40 marks. Okay. So that night I will close this assignment in Google Forms. You can write much before that also. It's up to you. So I will put this on Google Forms. I will put the other one on Google Forms. Whenever you feel like you submit it, I will not grade it. I will grade it only at that time. Okay. And yeah. So good. So I think that's it. We will not have the usual discussion session today. I will stop the recording and stop the meeting. If you have any question or comment, of course, you can get in touch with me either via Moodle or WhatsApp. WhatsApp meaning our group WhatsApp, so that your question, if I answer, everyone else gets to see the answer. So if anything is there, feel free to get in touch with me either on Moodle or WhatsApp, the group WhatsApp, MA521 group. And so that's the end of MA521. And thank you all for coming to all the classes. Most of the classes, most of you were there. In fact, I don't think I ever taught a course with this much attendance. So I am very happy with that. And so thank you all for making it lively, for coming to the classes. And of course, more than the classes, I have enjoyed our next half an hour, where I have talked to all of you and I got to know all of you, including various topics we have discussed. This is being recorded and this is going on YouTube. So therefore, I will not say what all we discussed, but you know what all we discussed. Yeah. So all the conversations we had in our breaks. So all the best. Yeah. So I will stop screen sharing. I will come on video. How do I stop screen sharing? Yeah. Stop screen sharing. So I must be on video. And whoever feel like coming on video, please do come. And I'm going to stop the recording. Otherwise, it's fine. It's up to you. Of course, I could have told you this before, so you could have been prepared to come on video, but I thought about it only yesterday night, so I didn't do that. Yeah. So if you have any comments to make, you make, and that's the end. Shall I stop recording then? Okay, so I'm stopping the recording. And